So now we will learn that what are the truth tables of the flip-flops. So first consider for the SR flip-flop. For SR flip-flop, when S equals to 0 and R equals to 0, the Qn plus 1 state or the next state will be the same as the previous state Qn, which can be 1 or 0, or this is called no change state. For S equals to 0 and R equals to 1, Qn plus 1 equals to 0, which is called reset state. For S equals to 1, R equals to 0, Qn plus 1 equals to 1, which is called set state. And this is the most important, that for S equals to 1 and R equals to 1, Qn plus 1 will be an uncertainty condition. There we cannot say that whatever it 1 or 0. Okay, this condition will remove, this uncertainty condition will recover or remove when we convert this SR flip-flop to the JK flip-flop. Now for JK flip-flop, for J equals to 0, K equals to 0, and for J equals to 1, K equals to 1, and for J equals to 1, K equals to 0, these first three rows are as same as SR flip-flop, but the last row where J equals to 1 and K equals to 1, where then the Qn plus 1 or the next state will be a toggle state. So what do you mean by toggle? That if the previous state was 1, then the next state will be 0, and if the previous state was 0, then the next state will be 1. So this is the truth table of the JK flip-flop. For D flip-flop, we will choose the second and third row of the truth table of the JK flip-flop. Then this is the D flip-flop, where you see that for D equals to 0, Qn plus 1 equals to 0 or the reset state, and for D equals to 1, Qn plus 1 will be 1 or the set state. Now for T flip-flop, we choose the first and fourth row of the JK flip-flop truth table. Here for T equals to 0, Qn plus 1 equals to no change state, and for T equals to 1, the Qn plus 1 is the toggle state. Now we have to make an excitation tables of flip-flops for all flip-flops. These are JK, T, and D flip-flops. Okay, so how can we make this? For SR flip-flop, first we see the truth table of the SR flip-flop. We already know this, and this is the excitation table of the SR flip-flop. So this is a very interesting thing. Here we consider the Qn or the previous state and the Qn plus 1 or the next state, and then we consider that what will be the S and R, the values of S and R for the Qn and Qn plus 1. Okay, so now in the truth table we got Qn plus 1, so here we consider Qn plus 1. This is important. So for Qn plus 1 equals to 0, here in the truth table, in the two cases Qn plus 1 equals to 0 for 0 0 and 0 1. So here we take 0 0 and 0 1 as Sn and Rn, and now we see that this 0 0, Sn is 0 and 0 in both cases, so 0 is confirmed for Sn, but here Rn is 0 and 1, so we don't know that whatever it will be 0 or 1, so we take Rn as cross. So the excitation table, in the excitation table, Sn and Rn will be 0 cross for 0 0. And in the same manner, similarly, we can do it for the state 0, 1, 1, 0 and 0, 1, 1. So for 0, 1, it will be 1, 0. For 1, 0, it will be 0, 1. And for 1, 1, it will be cross 0. To design a counter, you just have to remember it. The excitation table for most of the flip-flops. Here, the excitation table for the JK flip-flop, for D flip-flop and T flip-flop is given here. You just have to memorize it or remember it. Now, we'll go to the main section of our video. Now we have to design a Mod-9 synchronous counter using T flip-flops. So, there is some requirements or specifications of the Mod-9 synchronous counter, where as this is Mod-9 counter, the needed state will be 9. So flip-flops required is 4, because 9 is less than equals to 2 to the power 4, but greater than equals to 2 to the power 3. So we don't take 3 flip-flops, we have to use 4 flip-flops. But for 4 flip-flops, there are total states are 16. So invalid states are 16 minus 9 equals to 7. And this is the Mod-9 counter. Was you see that the arrows that for 0, 1, 2, 3, 4, 5, 6, 7, 8 and 0. We do not go to 9. From 8 we go back to 0. So this is an important state we have to table we have to prepare. PS is present state, NS is next state, and required excitations. Here required excitations for T flip-flop, because we tell that this is we have to use T flip-flop. So the excitations for T flip-flop. Now we'll see that how this table is made. So we have to know the truth table of the excitation table of the T flip-flop here. At the corner it's given, and below the required excitation. So for Q4, if we consider Q4, then at present state this is 4 and next state this is 0. Present state is Qn and next state is Qn plus 1. So for this, T should be 0. So here in the required excitations column at the T4, this is 0. Now similarly, for Q n equals to, or the present state, if 0 and the next state is 1, then the required excitations must be 1 according to the excitation table. Similarly for this 1 and 0, the excitations would be 1, and for 1 and 1, if Qn and Qn plus 1 is 1 and 1, then this required excitation should be 0. And similarly you can do it for these all states here. Now we have to draw the K-map diagram from excitation table. So this is the K-map diagram for T4. Here we take only T4. You have to do is for T3, T2 and T1 also. So for this we only concentrate on the T4 excitations. So here you see that in 7th and 8th row the excitations is 1 and 1. So in K-map you have to remember this is a short process. You have to remember the cell numbers, that is 0 1 3 2 4 5 7 6 12 13 15 14 8 9 11 10. This is a short process. You just see that at T4 column with in which position it is 1, and you just put it in the K map. Here 7th and 8th position have 1, so in K map we put 1 in 7th and 8th position. Now in mod 9 counter we only have 9 state, so invalid states are 7. 16 minus 40 flip-flop, invalid states are 7. So here 12 13 15 14 10 11 and 9 are the invalid state, and in K-map diagram we can choose it 1 or 0 according to our requirements, because these are the don't care position. So here we take for T4 this all cross as a 1. So the from K-map we can get this Boolean expression, reduced Boolean expression for T4 equals to Q3 Q2 Q1 plus Q4. Similarly, we get the expression for T2, T3 and T1 also, that is T3 equals to Q2 Q1, T2 equals to Q1, T1 equals to Q4 bar, and we all previously got that T4 equals to Q3 Q2 Q1 plus Q4. So the logic diagram of the synchronous mod 9 counter using T flip-flops is like this. This is the logic diagram, and this is the design, and that's how we can design it, the mod 9 counter. Okay, now take a look in the picture below. Now we take a look to the picture in details. These are the Boolean expressions we have to put here. Concentrate on this side. This is 3 equals to Q2 Q1, where Q1 and Q2 are ANDed and makes the T3 as Q2 Q1. And here in this part, T4 equals to Q3 Q2 Q1, where Q3 is ANDed with Q2 Q1 and make Q3 Q2 Q1, and we add a Q4 by the OR gate with this, and get the total expressions as T4 equals to Q3 Q2 Q1 plus Q4. Okay, so this is how we can make or design any counters with flip-flops.